All right, so today we're going to look at lesson 29. We're going to look at gravitational potential energy. We're going to look at kinetic energy and then conservation of mechanical energy. So hopefully after this lesson you'll understand gravitational potential energy, kinetic energy, and conservation of mechanical energy. The gravitational potential energy of the weight here with respect to the floor was 981 joules. The reason is because it had the ability to do that much work. The left weight could descend another 10 meters and raise the right one 10 more meters. And so then it would have done a total of 981 times 2, so 1962 joules of work. So that's how you have gravitational potential energy. You can have the potential to do energy just based on falling through the air. The gravitational potential energy of a mass depends only on its position above whatever your reference level is. So we chose the floor, or we chose whatever you want, flat surface. You just have potential energy based only on the position that it is above it. We can think of gravitational potential energy as energy that's stored just because of the vertical distance above the level that we designated. So it doesn't have to do anything, it's just the potential to move. So this is your formula. It's the weight times the height. Mass times gravity times height. That is your gravitational potential energy, which they usually write as just that. They don't actually write out gravitational potential energy. So let's look here. A 20 kilogram block is pushed slowly to the top of a frictionless inclined plane that is 6 meters tall. What is the increase in potential energy of the block? How much work is done moving the block up the plane? So it's a two-part question. So the first thing we need to do is figure out over here what the gravitational potential energy is once our block gets up here. So when it's on the floor, it has zero potential energy because it's on the floor. So the increase is just going to be whatever we get when we're up here. So it's mass times gravity times height. So our mass is 20, gravity is 9.81, and our height is 6. It's just how tall you are, not how far away from the point you went. So we went up 6. You get 1,177 if you multiply those, and we have 3 sig figs, so 1,180, and then joules. So that's the first question they ask. And then they also ask, what was the increase, or no, how much work is done moving the block up the plane? So we started here. They want to know, what is the work getting it up here? So they don't tell us anything. Oh, wait, no, they do. They tell us it is frictionless. As I say, they don't tell us if it's frictionless or not, but it is frictionless. So that means that there's no energy loss to friction on this problem. So all of the work done must also equal 1,180. And I'll show you how you can get that. It's going to be the same number, but just in case sometimes it's not going to be a frictionless, and I'll show you what you're going to do. So the work done is just force times the distance. So the force, remember we can draw our weight acting down, and then we can make our right triangle, and this is the x component, which would be 20 times 9.8, 1 times the sine of 30, because that's our angle degree. So that would be your force. And then the only other part you have to do is find the distance. And so the distance, you would use Pythagorean theorem to find the distance that they pushed it up. So if you use Pythagorean theorem with the 10.4 and the 6, you're going to get 12. So that's going to be your distance here. And then if you multiply those, you should get the same 1,177, which is 1,180 joules when you put it into the correct stick figs. So that's how much work is actually done moving the block up the plane. The work and the potential energy were the same on this one. So now we're going to look at kinetic energy, and that is the energy that is stored in the object because of its speed. So this is your formula for kinetic energy, 1/2 mv squared. So that's a formula you probably want to add to your formula sheet. So kinetic energy is energy due to speed, but like potential energy, it does not have direction. So it's not a vector quantity, it's just a scalar quantity. Work is a scalar quantity, and all forms of energy are scalar quantities, so you don't have to put a direction on work. So potential energy and kinetic energy are the two forms of mechanical energy. If you have a system that has no friction, potential energy can be converted totally into kinetic energy, and kinetic energy can be converted totally into potential energy. So that means that they are basically equal to each other, or able to be equal to each other. So when this occurs, we say that the mechanical energy of the frictionless system is conserved, because you don't lose any energy in a frictionless system. So let's look at this example. An 8-kilogram block slides from rest down a frictionless inclined plane that is 7 meters tall. What is the speed of the block when it leaves the ramp? So we need to figure out what the weight of our block is. They tell us the mass is 8. So the weight equals mass times gravity. Which is 78.48. And then the potential energy is your mass times gravity times height, which mass times gravity was 78.48, and your height was 7. So that's the potential energy that it had, 549.36. And we want to know the speed of the block when it leaves the ramp. So that's dealing with the kinetic energy. And so your kinetic energy formula is 1/2 mv squared. And so this number has to equal your kinetic energy, 549.36, equals 1/2 mv squared. Well, our m, we know that it is 8. And so you can solve for your v by dividing by 4. Basically, and then taking the square root of both sides. So we should get 11.72, which is, we're only using 2 sig figs, so that would round to 12 meters per second. You can also, if you would rather not have to work through it like that, your potential energy on these are going to equal the kinetic energy. And our potential energy formula was mgh, and our kinetic energy was 1/2 mv squared. And so you can set those two equal each other, and if you notice, the mass cancels out. So you really just have gh equals 1/2 v squared, and you can work through it using those formulas instead. So sometimes that helps people to do it this way over here. All right, we're going to look at another example. We have a 0.1 kilogram block or ball dropped from a height of 5, and it hits the floor with a bang and rebounds to a height of 4. What is its vertical velocity just before it hits the floor? What vertical velocity does it rebound? And how much energy is lost when it hits the floor? So let's start with A. So the potential energy that it has before it is dropped is the mass, which is 0.1, times the gravity, 9.81, times the height, which is 5. And so that's 4.905. And then just before it hits the floor, all of that has been converted into kinetic energy. And so we're going to use our kinetic energy formula. So all of our energy is now kinetic energy. And so just before, if you solve that, just before it hits the floor, the velocity is going to be negative 9.9 meters per second. We go to 2 sig figs because that number has 2 sig figs. And then it says, with what vertical velocity does it rebound? So it hits and then it bounces back up. On this one, the potential energy, the mass is 0.1, and then 9.81 is our gravity. The height, it only rebounds to a height of 4. So our height changes to 4. So our potential energy is 3.924. And so then we're going to plug it into our kinetic energy formula. 1/2 0.1 v squared. And if you solve that, you should get a positive 8.9 meters per second. Now, why is this one negative and why is that one positive? Well, on part A, we're going down. When we're going down, that's always negative. Part B, it's rebounding up, and we're going up, so that means it's a positive vertical velocity. And so that's what it rebounds with. And then how much energy does it lose when it hits the floor? Well, before it hit the floor, it had potential energy of 4.905. After it hit the floor, the potential energy was 3.924. And so if you subtract those, it's a difference of 0.981 joules. And so that's the energy that's lost from it hitting the floor. And that energy is used to make the noise that you would hear when the ball hits the floor, and a very, very small amount of heat that would occur from the two hitting each other. So that's where that energy goes. Because remember, energy can't be destroyed, it just gets moved into another form. Alright, so make sure that you do your homework 1 through 20 and the curveball questions so that we can go over any questions you have tomorrow.